morning. Welcome to Ray Summit 2025. Yeah, let's go. It's our fourth summit, so welcome back to those who have been here before, and a warm welcome to everyone that are here for the first time. Last year, when I attended my first Ray Summit, I had the opportunity to interact with a lot of you, and one quote stood out for me. Of all the conferences I've attended, this is the most concentrated gathering of AI and ML professionals that directly impact what I do every day. This was a direct quote coming from one of the senior attendees here in the audience. It's been a year since we met, and what a year it's been. Let's start by taking a look at the evolution of computing. We have had many eras, starting with the mainframe, going to client-server and enterprise computing, to the internet and web services, to cloud computing, and now the era of AI. Each era was unlocked by increasingly precise control of bits at larger and larger scales. AI is the next era, affecting everything from media to finance, from robotics to coding to search, self-driving, finance, space, pretty much everything. Make no mistake, the AI era is definitely here. As we look at the evolution of computing, each era was built on its own stack, on a new compute stack with a compute engine that powered that era. Starting with client-server and enterprise computing, the compute engine was a server powered by the likes of the Windows server or a Unix server, and there were many variations of that, Oracle databases and the like. Then came the internet and the web services era, where we had to virtualize the server into VMs to scale out. And on top of these VMs, we built the LAMP stack, as we affectionately called it back then. Linux, Apache, MySQL, and PHP. And then came the mobile cloud era, the cloud computing era, which was driven by microservices and big data. Here we added the container as the compute engine, and on top of that, we built services like Kubernetes, Kafka, Spark, Redis, MongoDB. I could go on. There's so much infrastructure software that was built in this era and still powers a lot of our platforms. But these transitions, while they look simple, were anything but. They were extremely disruptive. And many a times, many companies faded into the background because they were unable to navigate these transitions well. What separated the winners from the losers was how quickly you were able to adapt to this new paradigm and then build the infrastructure that powered this new paradigm. Names like Amazon that disrupted the art of selling books, or Netflix that disrupted how we watched movies, Uber that disrupted the traffic industry, the taxi industry, and Robinhood that disrupted how brokerage was done. These are just a few examples, and there's many more. And to be sure, these were great names too. They were not also-rans. They were real big brands of their time. The trap tends to be that what you have done, what got you here, is what is going to get you to the next level. You hear things like lift and shift as a very common term. I have invested a lot of time, money, energy, talent in building what I built already that's powering my stack. Why do I not take that and move it forward? Unfortunately, that never works out well. We saw that in the data center, taking lift and shift data center apps to the cloud, that didn't work. Moving desktop apps to mobile, that didn't work either. Running analytics on BI tools, that didn't work either. These are all examples of why taking an existing stack and trying to adapt it to the new era doesn't work. And the AI era will be no different. It will drive significant change and drive eventually its own computing stack. Here are the core fundamental reasons why. Number one, AI is built on heterogeneous hardware. It's not just about CPUs. It's CPUs and accelerators that come together to create your hardware layer. And increasingly, these accelerators are getting more and more powerful. They're getting interconnected with high-speed networking technologies like InfiniBand and Ultra Ethernet. They're enabling technologies like RDMA to really allow very fast context transfers between GPUs and TPUs and so on. And finally, the build-out of purpose-built specialized AI data centers is driving the AI-native computing era. Built on top of these are AI processing pipelines. Historically, we looked at pipelines like this. Data processing was a CPU pipeline. Training was a primarily GPU pipeline. And serving or inference was a matter of taking the model, hosting it on a single node GPU, and serving it out, and scaling it out as you would a microservice. What's happening now with the advent of multimodal data processing is the data processing itself is becoming a heterogeneous workload. Training, which used to be about pre-training a model, is now giving rise to the era of post-training and reinforcement learning, which is also becoming a heterogeneous workload. And serving is evolving from a single node GPU workload to a multi-node, much more complex distributed inference workload with the rise of reasoning and agentic AI. The models themselves, because of the scaling laws, are improving every day. It seems like there's a new model being released every day with increasingly more powerful capabilities. And these models are going to be at the heart of everything we do in the AI computing era. And finally, the way we build our systems is changing. Until now, all the systems we built were what you could consider deterministic systems. We would write our logic into code, create our microservice, perfect it, give it to prod, and then let prod takes it from there and gets it deployed. And then we move on to the next microservice. Well, AI is not like that. The heart of AI, as I said, is a model that is fundamentally non-deterministic in nature, which means once you put the model in production and start using it, you have to monitor it constantly. The words that come up a lot is evaluations. Alignment. Is the model performing in alignment with your goals that you set it out for? And evaluations are the way that you monitor models and their behavior. So it's not just a model of, it's not just about perfecting your code and shipping it. It's about constantly monitoring and ensuring that the outcomes are being delivered that you desire. It's about keeping that circle between data, code, and models going at all times. And the most important thing, the superpower that you must develop, is the ability to move fast. Iteration velocity is the name of the game here. And these four core drivers is what driving the emergence of a new AI computing stack. The core requirements for these, first is to be able to take the fundamental requirements of these workloads, the many parallel tasks that you need to run in real time, and dynamically orchestrate that across a cluster of CPUs, GPUs, and so on. Second, you need to have the flexibility in the compute engine to not only handle your workloads of today, but the workloads of tomorrow, to be able to evolve. Third, you need the fault tolerance to be able to run large jobs and services. Training runs can take weeks. Large batch inference jobs can take days. And you don't want these jobs to be interrupted. You want the fault tolerance in your compute fabric to be built in to ensure they continue at all times. And finally, the language of AI is Python. So any compute infrastructure that you address and scale and orchestrate needs to be Pythonic. This is what Ray was built for from the ground up. When Jan, Robert, and Philip started experimenting with reinforcement learning in their labs in UC Berkeley, the inspiration was this. And Ray is now, thanks to their efforts and the efforts of the community here at large, is firmly embedding itself as the compute engine of this AI native stack, powering not only AI workloads, but being the focal point integrating AI frameworks like PyTorch and VLLM and SGLang and many more. If you think of the evolution now, there is a new stack forming for AI native computing, and Ray is at the heart of it. This is why the downloads for Ray accelerated dramatically this year. Just this year alone, we have seen the number of downloads increase 5x. And it's because the workloads are getting more complex. It's a recognition of the reality that you need to build an AI compute engine that facilitates the new. All of you obviously have a huge hand in this. So I want to take a moment and thank you. We all feel deeply grateful at Anyscale and are humbled by the work and the inspiration that you bring every day and create amazing solutions using Ray at the heart of it. I want to take a moment and talk about a few examples. First, Grok. xAI is using Ray to build their models. Multimodal data is central to their effort, and they have built scalable high-performance data processing stacks using Ray Core to scale image and video data processing at massive scale in a fault-tolerant manner. xAI will be speaking about how they scale batch inference and multimodal data processing with lots and massive quantities of image and video data to prepare their training data. Next is Cursor. Cursor is building their leading agentic coding platform using Ray. Doing this involves scaling data processing, agents, evals, and reinforcement learning. They will talk about their stack, how Ray powers their infrastructure, and how they built their most advanced models. From the world of coding to the physical world, physical intelligence is a leader in building AI for robotics. Building AI for the physical world involves scaling data collection in the real world using large quantities of data, video data, robotic sensor data, and processing that to train these models. They'll be sharing how they build their generalist policies that can perform across different robotic embodiments and unstructured environments. So the big question in front of all of us is, how will you build your AI stack? The choices are straightforward. Option one, you could continue to extend the stack you already have. Option two is to build on top of frontier models. And option three is to create your own AI native infrastructure stack. Option one, as I discussed earlier, is about the innovator's dilemma. It seems very appealing because you already put a lot of investment into it. But by extending it, you lose the dynamism that you need to be able to orchestrate fine-grained tasks across a heterogeneous compute cluster, which basically means you start to underutilize your hardware, which are expensive investments, and most importantly, you won't be able to scale up for these new workloads, multimodal data processing, reinforcement learning, and distributed inference. The other option, which is to build on top of frontier models exclusively, is also limiting because you won't be able to tune these models for your specialized use cases. And that is what you truly need to do to deliver value to your organizations. Scaling lots of data, building agentic systems that use multiple models, all coming together. And to me, I think the most important reason is these transitions are an opportunity to build expertise, which is at the heart of navigating these transitions successfully. Every company, I remember the day when microservices came out, and we all thought that's only for the super high-tech companies. My software needs don't need microservices. Yet today, you can't find a software application builder that doesn't build using microservices. That same idea holds true for AI as well. You will be building AI, and it's important to build AI skills within the organizations. So the only real option then is about building an AI platform. But the question is how? I talked about Ray. Ray is at the heart of it, but there's a lot more to it. You need, of course, the cloud infrastructure, the compute hardware, and the frameworks that go with it. And then you need to bring it all together. You need to integrate this platform with frontier and custom models. You need to incorporate your dependencies, tooling for your developers. You need to boost performance. You need to make sure enterprise security policies are held together. Governance becomes important, especially with large teams. And finally, you got to be able to deploy in your cloud. This is what a unified AI platform is supposed to do. And that is our mission at Anyscale, to build out a unified AI platform that empowers every team to become an AI team and every developer to be an AI developer. Next, I'd like to bring Jon Stoika up to share with you a little bit about the founding origin story of Ray, as well as talk about why Ray's time is now. Please welcome Jon.
Please welcome to the stage Jon Stoika, co-founder and executive chairman of Anyscale.
Thank you, Keerti. Good morning, everyone. Thanks for coming. So next, I am going to tell you a story, the Ray story. It all started in fall of 2015 when two machine learning students, Philip and Robert, decided to take my class on big data systems. And they decided to do so because they wanted to learn how to build tools for their own research, because the tools at that time were hard to use and did not scale. And here is me with Philip and Robert, less than 1 year later, doing what any typical advisor does best: hands in pockets, interrupting students from doing work with annoying questions. At that time, if you remember, there was a lot of excitement around reinforcement learning. DeepMind and OpenAI demonstrated that RL can play computer games at the expert level and beyond. Google showed that RL can reduce the energy for cooling in data center by 40%. And of course, in 2017, AlphaGo shook the world by beating the Go world champion. And we are doing RL research ourselves. Philip co-authored with John Schulman, co-founder of OpenAI, a highly influential paper on Trusted Region Policy Optimization, or TRPO. TRPO is the ancestor of some of the most popular RL algorithms, including PPO and GRPO. And we are using RL for various applications, like teaching humanoid robots how to walk, improving traffic congestion, optimize database queries, and much more. So naturally, we build Ray for RL to support our own research. And here is RLlib, the library we built on top of Ray for scaling RL, the most complex workload at that time. Eventually, RLlib went to become the most popular RL libraries. But we are ahead of our time. While powering impressive applications, RL was slow to catch up. Fortunately, RL is such a general workload that building Ray for RL meant that it could support almost any AI workload. And here are the three canonical workloads powering AI: data processing, training, and serving, like Keerti mentioned. And there are three stages in the evolution of these workloads in the inceptions of Ray that have shaped the Ray's impact and adoption. And the three stages are classic deep neural networks and two phases of generative AI. The first stage involved dense neural models that typically process logs, such as user logs, to power applications such as recommendation systems. Data processing was embarrassingly parallel, primarily using CPUs. The models were small enough they could fit on a single GPU, so training used mainly data parallelisms to scale. And during inference, the main challenge was replicating the model on multiple GPUs to handle high request loads. Thus, while these workloads were distributed, they were relatively simple and moderate in scale, typically running on tens to hundreds of machines. As such, these workloads made limited use of Ray's full power and generality. And this was reflected in Ray adoption, which grew steadily but relatively slowly, taking 6 years to reach 500K downloads per week. The second stage, which we call the first generative AI phase, is defined by the release of ChatGPT nearly 3 years ago. And this stage kicked in the pre-training scaling law, which simply states that more data, larger models, and more compute predictably improve model performance. So no surprise that during this stage, we've seen a dramatic increasing in scale. Accordingly, the scale of data processing increased, though this workload was still confined to CPUs. And as models become larger, so they could no longer fit on a single GPUs. And as a result, new parallelism techniques emerge, such as tensor parallelism, to scale training. That said, most models, especially open source ones, were still small enough to fit on a single machine with multiple GPUs, which meant that the main challenge for inference remained to replicate these models on multiple machines to handle high request workloads. So in summary, during this stage, the workloads grew moderately in complexity, but dramatically in scale. This made Ray more relevant. For example, OpenAI used Ray as part of their stack to train ChatGPT. And this was reflected in Ray's adoption, which accelerated, growing from 500K to 1.5 million downloads per week in just 2 years. However, by the end of 2024, the scaling law of pre-training has slowed down. And in response, researchers turned their attention to post-training to further advance large language models. And this is a famous plot from the launching blog of O1, which shows that post-training, in this case reinforcement learning, can be as effective as improving model performance as pre-training. And we refer to this stage as the second phase of generative AI. In addition to post-training in this stage, we witness the rise of multimodal models that handle not only text, but video, images, and audio. And pre-training and multimodality together have driven a massive increase in complexity of the workloads. Data processing is no longer CPU only. It now uses a combination of CPUs and GPUs. Model architectures have become more complex with the emergence of a mixture of experts. Many models are no longer fitting on a single node. And this drove the number of parallelism techniques to scale up the training. Last time when I checked, there were no less than 7 different parallelism techniques. On top of that, inference adds more complexity with techniques such as expert routing, prefield disaggregation, speculative decoding, and more. Now, this is the complexity we build Ray for. The more complex the workload, the more Ray shines. And this is reflected in Ray's adoptions, with downloads exploding, growing nearly 5 times over the last year alone. So not surprisingly, today, Ray dominates some of the most demanding workloads. One example is multimodal data processing, which combines pre-training, post-training, and inference. Each of these stages have their different demands on compute and I/O. Pre-processing and post-processing typically works best on CPUs, while inference on GPUs. So fundamentally here, you need to run this workload on a large-scale heterogeneous cluster. Very complex. But Ray handles this complexity for you. And with the rise of multimodal data, like images, video, and audio, things are even more complex. Now the pre-processing and post-processing themselves might require some mix of CPU and GPUs. Again, Ray handles this additional complexity for you. The inference itself is becoming more complex, as I mentioned, with mixture of experts models. Different experts can run on different GPUs. With prefill disaggregation, tokens from the same request may spawn both CPUs and GPUs. And again, they can handle this additional complexity for you. And finally, we are coming full circle. Like I mentioned, one of the largest and most important workloads today is post-training. And the key component of post-training is reinforcement learning. And since we initially built Ray for RL, it should come as no surprise that today nearly every open source post-training framework is built on top of Ray. So, Ray's time has finally arrived. Ray's time is now. Next, please join me to welcome Robert, co-creator of Ray and co-founder of Anyscale, who will tell us about how Ray fits in the modern AI stack and will make several exciting announcements.
Please welcome to the stage Robert Nishihara, co-founder of Anyscale.
Thank you. Thank you, Jan. So Jan and Keerti talked about how complex AI workloads have grown with reinforcement learning, multimodal data, distributed inference. And they also talked about how complex hardware has grown with greater scale, heterogeneity, and failure rates. The sheer complexity at both the top and bottom of this picture have given rise to the need for a software stack that sits in between and connects the applications to the hardware. That software stack has to solve a huge range of challenges, ranging from scale to reliability. We've worked with hundreds of companies who are building out their AI infrastructure and have seen common patterns and common layers emerge in this stack. So I'd like to share the different layers that we've seen. At the top is the training and inference framework. This layer is responsible for running the model efficiently on the GPU. PyTorch is the dominant deep learning framework, and there's a rich ecosystem around PyTorch for parallelism strategies and transformers. But fundamentally, this layer is responsible for squeezing the most performance out of the GPU. Next is the distributed compute engine. This is where Ray sits. This layer is responsible for solving the hard distributed systems challenges of scaling. That includes process coordination and process management. It includes data ingest and data movement, failure handling, auto-scaling, resource management. All of this typically runs on top of a container orchestrator like Kubernetes, which is responsible for provisioning compute and handling coarse-grained multi-tenancy. So think user-level and job-level multi-tenancy. Now, as these layers have emerged, they've also been co-evolving with each other. And I'll give a couple examples. Jan talked about how complex distributed inference has become. Doing a great job with large model inference, it's such a hard problem. It requires doing a good job at multiple different levels of this stack. In particular, doing a great job with the inference engine and with process coordination. So the Ray and VLLM open source communities have worked very closely together to enable fine-grained placement of VLLM workers. So this has been essential for enabling cross-node parallelism strategies, prefill decode disaggregation, prefix-aware routing, wide expert parallelism, and a number of performance-critical optimizations. The Ray and Kubernetes open source communities have collaborated to enable new features like vertical pod auto-scaling for Ray workloads and more fine-grained application-level resource isolation. The reason these features require you to work at multiple levels of the stack is that they combine Ray's fine-grained awareness of what's happening inside of the workload with Kubernetes' ability to manage containers that are running the workload. So these are just two examples. The need for this software stack has grown a tremendous amount over the last year. So for that reason, Jan and Philip and I are very excited that Ray is joining the PyTorch Foundation. When we, yeah, thank you. So the PyTorch Foundation is home to foundational AI infrastructure projects. And when we started Ray back at UC Berkeley, from the very start, we conceived of Ray as a community-based open source project. So we're very excited to collaborate with the rest of the open source AI infrastructure ecosystem and really build out this stack. Next, I'd like to share a little bit about what the Ray community has been up to recently. So we've done a huge amount recently. We've merged 5,000 PRs in the last year. This is double the daily rate from the previous year. I'm going to start with Ray Core, because Ray Core is the foundation of the Ray ecosystem. What's changed is that over the last year, people have been running Ray at larger and larger scales. Not just at larger scale, but with less reliable hardware. That could mean spot instance preemptions, GPU failures, node preemptions, container preemptions. And not only instance failures, but networking failures. People are running Ray across multiple zones in situations with unreliable networking. And so RPCs can fail, TCP connections can be dropped, servers can be temporarily unreachable. Because of this, this is now the norm. Because of this, we've invested heavily in reliability at scale for Ray. What does that mean? We've hardened Ray's failure handling across the board. That includes making the Ray internal state machine idempotent, so it can handle retries at any point. We've invested in isolating Ray system processes from application resource pressure. Right? That's essential for reliability. And we've built a scalable observability stack. We've created an event export framework, so users can write events directly to persistent storage, which is necessary to remove the global control store bottleneck. So these are examples of things we've been doing. Reliability at scale has been a core theme. The other core theme I want to talk about is performance. We've seen a huge need recently for direct, accelerated GPU to GPU object transfer. This is important for reinforcement learning, where it comes up, you need to synchronize ship weights from training workers to inference workers very rapidly. It comes up in distributed inference for KV cache tensor transfers. It comes up in distributed training, especially really complex scenarios like non-uniform sharding of large multimodal models, where you need to ship activations and gradients around between different worker pools. And it also comes up in data processing for GPU to GPU data ingest and multi-stage data processing with large tensors. So this comes up all over the place. And this has to be really fast. So to support these workloads, I'm very excited to announce native RDMA support for Ray. Ray Direct Transport supports point-to-point transfer of PyTorch tensors between Ray actors. And we have a deep dive on this later today, which I encourage you all to attend. This supports RDMA-based backends, and it also supports collective-based backends. So to illustrate this feature, I want to actually show what it looks like in code. And to show it in code, I'm actually going to take a detour and first introduce the Ray Actor API, and then build up an example that uses this. So I'm going to show this through a reinforcement learning example. We've got two classes, a trainer for training the model, and a generator for generating new data using that model. And we need to synchronize the weights. So we have get weights and set weights methods. And Ray, at its core, is an actor framework. So it lets you add this ray.remote decorator. And now when I instantiate one of these classes, it creates a new actor process somewhere in the cluster with the appropriate compute resources. And you can start one of these. You can start 100,000 of these. They can invoke methods on each other, talk to each other. And with relatively little code, you have the building blocks for interesting distributed applications. So now to actually do reinforcement learning, we've got a couple parts. We're going to alternate between training the model and then generating new data. And to do that, we call train.remote and generate.remote. And that will kick off, send RPCs to the actors and kick off the methods. And in between, we're shipping the weights from the trainer to the generator by calling getWeights.remote on the trainer. And then there's an object reference, which is essentially a future, passing that into set weights. So the way this code is written here, the weights need to first be transferred to CPU memory and then shipped over the network. And depending on our use case, if we're running at scale, if we're using a large model, that's likely too slow. What we can do with Ray Direct Transport is add this line here, specify the transport backend, and now the weights will be shipped directly from GPU to GPU via RDMA. So improved RDMA support is super, super important for Ray. This is a direction I'm very excited about, something I'm excited for you all to try out, and an area we're excited to collaborate with the open source community on. Next, I want to share a little bit about the Ray libraries. And I'll talk about two different recent developments. First is the importance of multimodal data. We've seen an explosion of multimodal data over the last year. And we've invested in making Ray data the most powerful multimodal data processing engine. Right? That includes great handling of large tensors, handling of large cross-node multimodal models for batch inference, heterogeneous data types, and purpose-built multimodal data formats. And doing this has led to significantly improved faster reads and higher throughput for aggregation, complex aggregation-heavy workloads. Right? So there's a tremendous amount of work going on here, and we think multimodal data is just getting started. The second development I want to share is something everyone here knows, which is the growth in model size. And this is what has led us to invest in shipping a huge range of features to better support large model inference, ranging from prefill, decode disaggregation, prefix and LLM-aware routing, custom auto-scaling, wide expert parallelism serving patterns, and a huge range of other optimizations for both online and offline inference. And I expect these two trends to just continue. But these are just two examples of what we've been up to. I'm not going to list everything, but we have 8 deep dives at this conference today and tomorrow covering the Ray internals, the roadmap, and what the team has been up to recently. The last thing I want to call out is that there is a rich ecosystem on top of Ray. You've probably heard of a number of these different projects. We've seen an explosion of new projects, ranging from AI Bricks from ByteDance to Nemo Curator from NVIDIA to Slime from Z.AI. These are RL frameworks, agent frameworks, inference frameworks, data frameworks. Many of these projects will be speaking here today and tomorrow. And these teams are doing incredible work. And this is what makes Ray powerful. It's the presence of such a rich community ecosystem on top of Ray. So thank you. Next, I'd like to invite Keerti back to the stage to talk about the Anyscale platform.
Excellent. Well, next I want to change hats and move from open source to Anyscale. As I mentioned earlier, the requirements for an AI platform are beyond the stack. You, of course, need the stack itself, but you need to be able to productize the stack, which means integrating your models, incorporating your dependencies, creating your developer tooling, boosting performance, security policies, governance, deployments, and more. And this is what we built Anyscale for, to be the unified AI platform that empowers you to go make your AI models, your AI products come to life. Thanks to our adoption from our community, you have embraced Anyscale very warmly, and I'm very excited to announce that Anyscale has grown 10x in revenues over the last 8 quarters. And these are just a few example customers that we are showing here on the slide. I want to take a moment to walk you through 3 key examples. First is TripAdvisor. Many of you probably use TripAdvisor to plan your trips. They use customer images and vast amounts of it in a batch inference mode to then feed their recommendation engines when you do your searches. Those 2 stages were disparate before. The batch inference stage was done differently than the online inference part of it. With Anyscale, they were able to unify both of those stages together and lower the cost of batch embeddings by 70% and reduce their code sprawl by 80%, really modernizing their inference platform within TripAdvisor. Coactive is a startup. They're a multimodal intelligence platform for media companies. And they used to take weeks to be able to transition from development to production. And with Anyscale, they were able to reduce that time to a single day, to take something that they developed and put it in production. And using Anyscale, they were able to lower their costs by 4 times and GPU compute costs by 75%. Nubank, which is a large bank operating out of Latin America, they are transitioning to an AI-first future for their customers. They use Ray Train and Ray Data on Anyscale to train their own internal transformer model. They are transforming their own company from that cloud-native company to an AI-first company and delivering superior experiences for their customers using their transformer models. So these are just a few examples of how customers are embracing Anyscale. We'll dive deeper into the platform and some exciting new announcements coming up on the Anyscale platform. To do that, let's welcome Jaikumar Ganesh, Head of Engineering, up here.
Please welcome to the stage Jaikumar Ganesh, Head of Engineering at Anyscale.
Thank you, Keerti. How's everyone doing? Race time is now. I want to amp it up further. Please stand up. All right. So on a count of 3, 2, 1, we are all going to say, let's go, Ray. 3, 2, 1. Let's go, Ray. All right. Once again, louder. 3, 2, 1. Let's go, Ray. That's the spirit. Let's go, Ray. Please take a seat. So Keerti talked about the impact customers like TripAdvisor, Coactive, and Nubank are having with the Anyscale platform. So what is this Anyscale platform? It primarily consists of these 3 main layers: Developer Central, Ray, and Cluster Controller. We have worked with many Ray users and Anyscale customers, and we have a clear idea of the Ray adoption journey. Getting started with Ray is very easy. You just download Ray on your laptop, and you're up and running. But when you go into multi-node development, challenges start to appear. You now need to propagate dependencies to all the nodes of the cluster. You need observability. You need monitoring. You need debugging tools to figure out all the worker logs in all the nodes. And then you have taken this workload to production. And when you go to production, you need to handle all the clusters. You need to upgrade them. You need to understand the cloud provider stack. You need monitoring. And when you have a workload that's running, you want it to be fast. You want it to be cheap. You want to be reliable at scale. And once you're there, you want to expand Ray usage to all other teams within your company. That's not easy. You need to first train them on Ray. Then you need to take care of cost controls, governance features, audits, budgets. You need a way to track all your model versions. You started with Ray. You learned Ray. Now you have to solve all the problems around Ray. That's not easy. That's why we built Anyscale, fully managed, production-ready platform. But the beauty of Anyscale comes in when all these 3 layers work in unison together. That's the magic. What do I mean by that? Let's take an example. You have a training workload. You're training a model across thousands of GPUs. You need observability to deeply profile GPU metrics. You need a job framework to kick off your training workload. You need checkpointing and mid-epoch resumption so that when your train job fails, it can restart from the same point. Your infrastructure needs to provide GPU health checks so that it can get rid of all the bad GPUs from the cluster. You need capabilities like GPU search capabilities in multi-cloud and multi-region so that you get the best GPUs. It's all these 3 layers working together that's going to power your platform. Let's take 2 customer examples. Geotab, an AI-first fleet company. They use large amount of video processing data to improve driving behavior, optimizing fuel efficiency, and road safety. They weren't able to find any system that is going to serve their needs. So they used all the 3 layers of the Anyscale tech stack: observability, the runtime, the cluster controller layer. They were able to see 43x better throughput, 40% reduction of GPUs at peak. Prenovo, another AI-first preventative healthcare startup. They want to collect a lot of multimodal data, petabytes, and they want to do anomaly detection, biomarker correlation. They also used all the 3 layers of the tech stack: observability, the runtime, cluster controller. Developer startup time improved by 5x, and they were able to reduce costs by 40%. They were able to do this at petabyte scale and also handle the security and compliance needs of the health sector on the Anyscale platform. That's the power of Anyscale, the 3 layers working together. So now let's deep dive into each one of these layers. Let's start with the Anyscale Runtime. What's this Anyscale Runtime? Firstly, it's fully compatible with Ray open source APIs. If you have an application working in open source, it's going to work on Anyscale. It's an evolution of the project we announced last year called Ray Turbo. We battle tested it, made it more reliable, worked with all the customers, and made your workloads faster, cheaper, and reliable at scale. We worked every stage of the pipeline, from reading of data to auto-scaling to checkpointing. But all of you are developers and engineers. You're not going to trust me. You'll say, show me the benchmarks. To do that, I'd like to invite Richard Liao onto the stage.
Please welcome to the stage Richard Liao, founding engineer and product manager at Anyscale.
Thanks, Jay Kumar. Last year, we announced Ray Turbo. And this year, we're evolving Ray Turbo into Anyscale Runtime. In Anyscale Runtime, we've optimized the 3 canonical workloads that Jan talked about: data workloads, training workloads, and serving workloads. Now let's deep dive into each, starting with data. Great models require great data, and great data requires great data processing. Data processing workloads for AI often have unique requirements. First of all, they need to maximize throughput. They also need to work with multimodal data, which includes structured data, images, videos, text, audio, so on and so forth. And finally, they also need to work with the great accelerator ecosystem that we have today, including CPUs, GPUs, but also TPUs and other chips as well. And we've optimized Anyscale Runtime's Ray data to address these requirements. Within Anyscale Runtime for Ray data, we've improved data reading and writing for key data formats, including Parquet and JSON. We've re-implemented various operations to take advantage of vectorized compute kernels. We've re-implemented our autoscaler so that it can be much more responsive and better efficient. These changes can lead to significant performance improvements over open source Ray. Let's take a look at how this impacts some customer workloads. A couple customers we worked with had multiple terabytes of data stored in their data lake of images. And these pipelines were fairly similar. They would read the data, transform it on CPUs, run the inference using a vision language model on GPUs, and finally write the results back into storage. And what we did was we compared this, running the same exact pipeline using open source Ray and Anyscale Runtime. On a fixed capacity cluster, running the same pipeline on Anyscale Runtime delivered about 2x faster performance compared to open source. Then we enabled our optimized autoscaler in Anyscale Runtime, and that single change made the run 6x more cost efficient without any tuning or manual intervention. So you might say, OK, well, this is a very specific workload. But we also took other common workloads, and we saw similar performance enhancements. Anyscale Runtime was measured to be about 10 times faster for select feature preprocessing workloads. Anyscale Runtime was measured to be 2.5 times faster for select TPCH queries. Now, beyond data, Anyscale Runtime also has major features for training reliability as well. Training workloads are very notoriously hard to scale well, especially when you have GPUs that fail all the time and data loading that can be really prone to out-of-memory issues. And Anyscale Runtime addresses these exact problems. With dynamic memory management, Anyscale Runtime can automatically set task memory requirements, reducing spilling and out-of-memory issues for training data loading. With mid-epoch resumption, Anyscale Runtime enables you to pause and resume training when you're using large data sets. Elastic training allows training to continue even under preemptive nodes. And GPU profiling on Anyscale Runtime provides in-depth observability into accelerator health and utilization. This, in conjunction with all the other parts of the Anyscale stack, solves many training reliability issues that we see in production. Now, let's take a look at serving and online inferencing as well. Online inferencing systems have a unique set of requirements. And in particular, compared to any other workload, SLAs are key. However, as online inferencing systems continue to evolve, they also need to handle multimodal data, and they also need to handle heterogeneous hardware. And to solve these issues, the team has optimized critical parts of the Anyscale Runtime serving stack as well. In Anyscale Runtime, we've implemented a faster transport layer for large object transfers. We've optimized our ingress layer to improve scalability and throughput, and we've implemented replica compaction for efficient and cost-effective autoscaling. Let's see what this means for real-world serving pipelines. So working with customers, we've seen multiple pipelines that leverage both CPUs and GPUs for online inferencing with models. And taking a representative pipeline that we've worked on with some select customers, Anyscale Runtime was able to achieve 7x higher throughput on the same hardware and latency constraints compared to open source. I've talked about a couple of these workloads in depth, but Anyscale Runtime is actually much more broad and much more deep than what I can cover here. We've done optimization work across a wide variety of AI workloads, working up and down the stack. And you can find out more about this and reproduce the results on our GitHub. We also have a roadmap for many more critical workloads. And our goal for Anyscale Runtime is to be the best compute substrate for any AI workloads out there. Now, to show you how easy it is to use this very, very powerful runtime with all the great developer tooling that we have on Anyscale, let's hear it from Goku and Akshay.
Please welcome to the stage Goku Mohandas from Ray Noob and Akshay Malik, Ray Expert.
Yo, Akshay. So I'm a Python application developer and honestly a bit of a Ray noob as well. And I've been wanting to build this agentic application where I can ask any question I want about any kind of video, a trailer or an entire movie. And I started to build it out, and I already started to hit a bunch of bottlenecks. There's so many different models I need to use that don't fit on my machine. And even just a few minutes of video involves tens of thousands of frames. Do you think you can help me build it and also scale it out?
Yeah, of course. I'm a big-time Ray expert, as they just said. So I can definitely help you out here. Tell me more about your application.
OK, so here's the super high-level architecture. I want to start off with some pre-processing. So let's say we start with a video, and I want to be able to extract the audio and also the visual frames. Then I want to kick a whole series of batch inference workloads where I take the audio, generate transcripts, and also embed those transcripts so we can search semantically. And I want to do something similar for the visual frames as well. Finally, I want to have some kind of agentic workflow on top because some questions maybe just require the transcript, some just the video, and some maybe multimodal and requires everything. Now, how do we build this and actually scale it out?
So I actually had the foresight that you would be asking me this
really?
exact question during the keynote today. So I built out Rayflix for you. Let's give it a go.
OK, I was actually just backstage, and I was talking to Jan, our visionary founder, and he was just telling me about this next big thing, K-pop Demon Hunters.
Jan said that.
Yeah, he was really into it. So I don't really like scary movies, so are there actually real demons in this movie?
Let's test that out.
I mean, it's meant for children, but let's see. Yikes.
Looks like there's some real
OK,
demons.
so it looks like both the transcript and video found matches. I think I'm going to give it a shot anyway, because Jan usually has a good intuition for these kind of things.
Yeah, you should.
OK. So I want to ask a bunch more questions about some of my other favorite movies. But maybe you can first tell me about how you did this. How did you scale this? Where did you build it? How did you put this together?
Yeah, so I started in Anyscale workspaces. So Ray always had like a laptop-friendly development experience in mind. But with Anyscale workspaces, we can create this infinite laptop experience seamlessly on any cloud. So here I have my dependency management, my Ray data code, and really everything I need to develop and debug at scale.
Nice. And then just double checking, but did you get all of my thousands of videos from Azure Blob Storage, metadata from Unity Catalog, and data from everywhere else too?
Yeah, you should trust me, bro. So Ray data can read from virtually any data source. And on Anyscale, we have these easy one-click integrations into popular data catalogs like Databricks, Snowflake, or really wherever your data is being held hostage.
OK. So this sounds pretty cool. Now, I know you're a Ray expert, but I've heard that working with distributed systems is not only hard, but extremely difficult to debug. Are you telling me that nothing went wrong during all this?
I messed up a few times. But with Anyscale observability tools, I could figure out exactly what was going on. So metrics, logs, tracing, all in one place. There was also this really cool Ray data dashboard. So this gave me contextualized information for Ray data workloads. So I can see my execution graph here. I can see the throughput, the errors at each stage. So I can really optimize my Ray data pipelines.
Nice. This looks extremely comprehensive, but it also looks like a ton of information thrown at me at once. How do you know where to look when something specific happens, like, say, an out-of-memory issue?
Yeah, Anyscale has thought through that too. So there's these critical events that show up. So things like out-of-memory errors, failed nodes. And then I can click on this and get some guided fixes on them.
Nice. OK, I get a pretty good idea of how you developed and debugged this. But how did you go from here to actually kicking off all the different batch inference workloads on top of the thousands of videos?
I used Anyscale jobs. So with Anyscale jobs, think of them as ephemeral Ray clusters. I can schedule jobs. I can integrate with any orchestration tooling of my choice as well. So I can really scale out my data processing.
OK, and these jobs, though, don't they have a ton of different artifacts? For starters, we've loaded data from so many different places. We're using so many models for the batch inference, like Whisper and Clip. And obviously, we're generating a lot of transcripts and embeddings. How do you keep track of all these different artifacts?
Yeah, it got a little tricky, to be honest, to track all these different data sets and models. So today, we are launching lineage tracking on Anyscale.
That sounds like a pretty big deal, to know out of the box where your data models are coming from and where they're being used.
Yeah, it is such a big deal that we have to move to a big slide. There we go. So with lineage tracking, we can track all model and data transformations automatically. So that V3 final model that you kind of YOLO shipped to prod last week, I know exactly what data went into it.
Just to be clear, I don't name my models, that kind of stuff.
No one should.
OK, so this is very cool. And I get how you did the preprocessing and batch inference using a combination of workspaces, jobs, and some of the awesome tooling. But what about the real-time service, though? I feel this is almost a little too complex to even architect. So I want to start with the query. I want to serve an open source LLM that can look at the query and come up with a series of actions or plan. And each of these actions basically are independent tool calls. And think of them as retrievals on top of the data that we just generated from the batch inference. So ability to search through the transcripts, search through the visual frames, and even some multimodal logic as well. And then I want the same original LLM to use the outputs of these tool calls to generate the response. How do you build something like this? And then am I going to get some kind of ridiculously large bill for all the idle GPUs that you've involved?
No GPUs were wasted in this production. So with Ray Serve, I can easily convert these different components that need to scale independently into Ray Serve deployments. And then I can deploy it all together as part of one application.
Nice. And then you were able to incorporate that agentic logic as well?
Yeah, absolutely. I can build my own dynamic inference graph all in Python in one place. And then I even took it to production using Anyscale services. So think of Anyscale services as this like fully production-ready endpoint. So it gives me things like zero downtime upgrades, observability, A/B testing. It gives me complete peace of mind in production.
OK. Actually, I've got to say, I think I'm pretty convinced that Ray is extremely powerful. But I still feel, at least even without the help of a self-proclaimed Ray expert like yourself, I'm going to be pretty overwhelmed still, converting my workloads to Ray, debugging them, and I'm not even thinking about optimizing yet. How long did it take you to do all of this?
Took me just 2 days.
2 days for an expert.
That's it.
OK. I got to come clean about something. I was actually testing you this whole time to see if you actually knew what you were talking about and if you were an expert. I ended up building something extremely similar to this in just a couple hours.
Oh, really?
Yeah, and I did it using our internal Ray development agent that we've been building. I'm sure a lot of the audience here has already been using, hopefully, tools like Cursor and Claude to work on their and develop and debug their Ray workloads. But we started to build something internally where, think of an agent that sits on top of something like Cursor, but beyond just having access to your code base, it has access to live documentation, whether it's Ray, Anyscale, or all the other libraries you're using. It has access to a growing and live updated list of best practices to use, anti-patterns to avoid, and also some contextual things like your specific cluster, what resources you have, what are the things you're trying to optimize for, what are the relevant metrics, logs, and events that are important to your workload, and even historical information from maybe prior runs. And using all this, we can actually generate working Ray code where we can test it on a small batch. And yeah, I think this is a great way to actually get started and convert your workloads, debug them, and optimize them.
So anyone can be a Ray expert?
Yeah, pretty much. With the guided observability you showed, the data and MLOps integrations, the whole dev to prod experience, and now with agents on Anyscale that we're going to be rolling out soon, yeah, I really do think that everyone can start to become a Ray expert.
That's great. And all this without having to worry about infrastructure either.
Exactly.
So let's bring back JK to talk about how all the infrastructure magic comes to life.
Thanks, Akshay and Goku. I love Unity catalog integration and lineage tracking. And Goku, we need to talk. I just got a message from our on-call about the V3 final service you launched. All right, so let's peel the third layer, the cluster controller layer. This manages end-to-end compute lifecycle management with sub-minute cluster startup time, upgrades, intelligent auto-scaling, and multi-cloud, multi-GPU features. Governance layers gives you cost controls, budgets, to make sure you're able to scale and keep your finance and security teams happy. Last year, we made 2 big announcements. First was Kubernetes GA on Anyscale. And I'm actually very happy to see strong adoption, 20% month over month. We also made it easy for people in OSS to convert to Anyscale. Today, I'm super excited to announce our deep collaboration with the Google GKE team. Anyscale and the GKE team are working closely to bring the power of Ray and Kubernetes together to envision the AI stack that Robert talked about. We are working on features like label-based scheduling, resource group isolation, in-place pod resizing. This gives you fast startup times for tasks and actors. It gives you better bin packing, improved reliability by reducing OOMs. And on a particular workload, we saw 30% more gains because we scale vertically first before going horizontal. This is a big deal, and we are going to invest a lot more in this area. The second feature we talked about was budget controls. This is a feature that is also getting a lot of love. And today, we are announcing even more capabilities in this area. Resource tags, which makes you easy to do cost attribution, cleanup, and filtering, and a brand new invoicing dashboard so that you can track your costs. Compute efficiency is an area on top of everyone's mind. GPU availability is an issue. GPU utilization is an issue. And we have been hard at work in this area. To talk more about that, I would like to invite Elizabeth Hu onto the stage.
Please welcome to the stage Elizabeth Hu, Product Manager at Anyscale.
Thanks, JK. So this time last year, the industry was searching everywhere for spare GPU capacity. Sometimes there wasn't enough capacity in a region or even in the entire cloud provider, and you just needed to get an H200 wherever you could get it. Anyscale has always been designed to support multiple deployments of clouds, where a single customer can run across regions, cloud providers, or even different compute stacks. So we thought to ourselves, why does an Anyscale cloud need to be tied to one set of resources? Couldn't we look across different resources to see where we could find capacity? To solve this, we're introducing the next generation of deployment, multi-resource clouds, now available in beta. Anyscale takes care of the infrastructure complexities of running multi-region or multi-cloud for you. Anyscale intelligently searches across registered resources to meet your workload's requirements, all with a uniform way to express your resource needs. Multi-resource clouds let you hook up multiple cloud resources to one Anyscale cloud. These can be in the same cloud provider but different regions, different cloud providers, or different compute stacks. Let's say, for example, you really need to get a job done and it requires an H100. Anyscale scans across your registered resources until the necessary capacity required is available to then seamlessly deploy your job. And this is just one more way in which you can unlock flexibility to run AI workloads without worrying about the infra. But now, even if I manage to get a GPU, people are now facing a slightly different challenge. It's not only can I get GPUs, but how do I share capacity amongst my team with competing priorities while getting the highest utilization possible? And GPU reservations sound great until they aren't when those GPUs sit idle while jobs wait in line to run. They also lack awareness of the workload and aren't easily able to burst out of the preset capacity. The result, underutilization, frustrated teams, and wasted budget. Imagine instead a global resource scheduler that understands your workloads, your reservations, and your priorities. That's what Anyscale's global resource scheduler is. GRS lets you effectively allocate and prioritize constrained resources across all RAY clusters across your Anyscale clouds. GRS allows you to create partitions and define rules for all types of compute, including reservations, on-demand, and spot. Let's say your company has invested in an H100 reservation for running training, inference, other GPU-intensive workloads. Now, typically, teams statically partition that reservation, one part for training and the other for inference. But that's inefficient. Inference has to be sized for peak load, leaving GPUs idle, while training jobs sit queued waiting for capacity. Anyscale's global resource scheduler solves this problem by allowing flexible prioritization across all workloads on your GPUs. In my reservation, for example, I'm running a production inference service, and my researchers are launching training jobs. Now, inference traffic can get variable, so one day many more users query my service. GRS is able to preempt lower priority training jobs and allocate those GPUs to inference. And as load increases, we'll continue to preempt lower priority jobs and shift those GPUs over to the higher priority inference service. The other way around, as traffic falls, GRS is able to move those workloads back and resume from where they left off. We can even use idle capacity for some background jobs like data processing to soak up the idle compute. GRS works beyond reserve capacity as well. It can tap into spot and on-demand GPUs. If a job is preempted, GRS can find available compute elsewhere and keep it running. So with GRS, you get higher utilization without sacrificing dev productivity, saving money, and getting you the most out of your reservations. All of this is progress on our goal to support any workload, any cloud, any accelerator. And this is why we've worked to unlock capacity with our partners on AWS, GCP, CoreWeave, and Nebius. However, we wanted to unlock Ray particularly for the enterprise. And that's when our partners at Azure approached us after seeing an uptick in Ray among their customer base. The message was quite clear. Azure customers wanted open source flexibility without cluster management overhead, and they wanted it all tightly integrated into their Azure ecosystem. So we're very excited to announce Anyscale on Azure, now available in private preview. Anyscale on Azure is a dedicated deployment of the Anyscale platform, tightly integrated into Azure infrastructure as a first-party native service. With this Anyscale and Microsoft co-engineered integration, you can manage Anyscale from the Azure portal, pay for it using your Azure commitments, and use Entra ID to manage access controls, directly deploying your workloads on AKS to securely run your AI next to your data. Let me show you a quick demo. From the Azure portal, you can deploy and manage Anyscale as a first-party service, just like any other Azure resource. So under the AI category, I simply select Anyscale to get started. Now let's deploy a cloud. I'll create a new Anyscale cloud, and through a click-through process, all I have to do is assign a subscription, a resource group, choose a region, and give my cloud a name. As a next step, I'll specify cloud storage, where I'll want to grab data from. Under the hood, Anyscale is deploying the Anyscale operator as an AKS extension, so you don't have to manually install Helm charts. And as a reminder, the Anyscale operator manages the relationship between the Anyscale control plane and your Kubernetes cluster. Now, your cloud is almost ready to use. If you needed to, you could also adjust things like access controls, tags, and other settings directly from the Azure portal. And because Anyscale is running entirely inside of Azure's security framework, authentication and authorization happens seamlessly through Entra ID. So as a developer, I'm logging in, and once I've logged in, the rest of the experience looks and feels just like the regular Anyscale UI. For example, I can start up a workspace for interactive development, where I can configure the instance types for my head and worker nodes. Once that's launched, I can start to see AKS pods getting scheduled. And just like any other AKS pod, now I can go to the Azure portal and monitor status and other metrics directly from there. Now, going back to our workspace on Anyscale, I can start to do development for things like a multimodal data pipeline. And here you can see how easy it is for me to start getting working by using data already pre-configured in an Azure Blob Store. So yes, it's very easy to get started in a way that's both scalable and secure from the start with Anyscale on Azure. To talk us through the partnership and how we made this successful, I'd like to welcome to the stage Keerti and Brendan Burns.
Please welcome to the stage Brendan Burns, CVP, Microsoft Azure Cloud Native and Management Platform.
Welcome, Brendan.
Thank you so much.
Great to have you here at Ray Summit.
Yeah, for sure.
Well, you are one of the OGs of Kubernetes, co-creator, co-founder. Your name is on the wiki page. I looked it up.
That's right.
Share a little bit about the early days and maybe draw a parallel to what you're seeing today.
Sure, yeah, I was reminiscing actually about the very first KubeCon. KubeCon's coming up next week. But the very first KubeCon was here in San Francisco in a room about this size about 10 years ago. And you know, that sense of energy and the hockey stick of downloads that you showed earlier, it's very reminiscent of that experience. And so you know, I'm very optimistic that the kind of community that we built worldwide with Kubernetes is the kind of community that's forming up right now. And I look forward to Ray Summit being scaled out in 10 years.
Oh, those are inspiring words, mate. I'm very excited about that as well. Well, you talk in your role at Microsoft to a lot of enterprises.
Yeah.
So maybe talk a little bit about what trends you're hearing when it comes to AI.
Yeah, I mean, I think everybody started out with, we need to figure out how to AI our business, maybe 2 or 3 years ago. And so a lot of it was just talking about, like, what are the opportunities to embed AI into the business. But I think now, as we're entering, maybe the real productionization part of it, what we're seeing is, the business is actually what's the most important thing. The AI is in support of the business. And so people are trying to figure out, how do I build the right models in addition to combining them with foundation models? How do I think about cost control? How do I think about security and reliability? And all of these concerns that come with actually shipping something that go out to a banking customer, an insurance customer, these regulated industries. So we're helping people through that, and we think these open innovations like Ray are essential components in how we deliver that platform or help customers build that platform themselves.
Do you see the conversation about should we build an AI platform or should we just call an API endpoint come up?
Yeah, I mean, I think, obviously I'm on the infrastructure side within Azure, and so we talk to a lot of customers in some sense who've already decided they want to build their own platform, but they're thinking about how do I blend a mix. I don't think it's a either or, and certainly our aspiration is not for it to be an either or, but rather a blend where there's going to be use cases, there's going to be prompts that work really well with foundation models where you're paying per token. And there's going to be places where you want to run your own models for fine-tuning or because that's the right cost versus value trade-off, even all the way down to CPUs, or you want to have the same infrastructure at the edge. I think hybrid AI is another area.
That's a good term.
Really
hybrid
critical.
AI is exactly what we're seeing as well. So talk a little bit, in terms of infrastructure, Ray and Kubernetes working together.
Yeah.
How do you see it?
Well, I really think that, I was thinking back to the keynote that I gave, and it was all about democratizing distributed systems. And I think the same thing with Ray. You need to provide. I looked at that decorator that was adding, that was being shown earlier, that added RDMA support for communicating with GPUs. That's one line of code, right? I guarantee you there's not one line of code behind that ease of use, right? So providing that ease of use for people to be able to access the core technologies that they need to build the applications they want to build, I think that's a fantastic thing that Ray is doing, and I see the same analogs in Kubernetes.
Awesome. Let's talk a little bit about the partnership.
Yeah.
Anyscale, you called us, I want to say 6 months ago now,
right.
And we've put together this partnership, excited about it.
Yeah.
I'd love to hear your words on it.
Yeah, I think there's 2 really important parts about any partnership that we do, and this partnership like that. The first is we have to have customer interest, right? There has to be people out there who are already using Ray on our platform or already using the software on our platform. And in this case, we talked to a bunch of customers. They're already using open source Ray, right? But of course, a lot of our customers, and I think every customer, wants it to be supported, wants to be able to call my team and any time of day and get help with it. And so that's where the managed solution comes in. And then also, I think, as a cloud platform, we have an obligation to not just ship our software, but provide the best of breed across the world, and especially in the open source world, enabling people to build software businesses on top of our platforms. And so that combination of customer interest and our desire to build a broad platform led us to the partnership, and it's been great.
Awesome. Microsoft's reputation as a partner is legendary, and we are so excited to be that first-party service on Azure, helping you, supporting you in scaling, and helping you scale your service as well.
Absolutely.
So maybe a quick takeaway before we take a break. You've seen obviously the development of Kubernetes, development of Ray, AI-first companies coming up. What's the takeaway for the community?
Yeah, I think my takeaway for the community here is that I think a lot of people in the room and a lot of people in that first room back at the first KubeCon, you're excited about the technology. You're excited about AI in this case and the details of inference and all this sort of thing. But at the end of the day, the most successful platforms are the platforms that empower the most users. And I see that resonating in what we try and do throughout all of Azure, and what I was trying to do when we stepped onto the stage at that KubeCon. We said, I'm really trying to democratize distributed systems. And I think that we've made a lot of strides in that goal. And my suggestion to you and the broader Ray community is, if you want to achieve that impact, think about how can you democratize AI out into the world? How can you make all of these tools and techniques that are revolutionizing the things that you're building today available to 10 times the number of developers tomorrow, or 100 times the number of developers in a few more years? And if you do that, you're going to build a really successful community, and you already have. And so I really would take that inspiration around democratizing AI.
Awesome. Well, thank you very much. Really appreciate it. We are inspired and looking forward to partnering closely.
Thank you so much. Have a good day.